Hi, I'm Jorge Mendez, and this is work on lifelong policy gradient learning of factored policies. PG methods have enabled learning continuous control policies for high-dimensional dynamical systems. Unfortunately, they typically require extensive interaction with the environment. If the agent is faced with multiple consecutive tasks, it should leverage information from previously learned tasks to accelerate the learning of new tasks. We created a lifelong policy gradient method that enables faster training, completely avoids catastrophic forgetting, and achieves lifelong transfer on the recent MetaWorld benchmark. Most existing lifelong RL methods share a policy across tasks, enabling rapid adaptation to closely related tasks. However, the model typically becomes saturated after only a few tasks. Other techniques learn a collection of models that can be combined in different ways to learn more highly varied problems. The multiple models are typically learned by first training individual policies on each task separately and subsequently combining information from the various tasks to achieve transfer, so the learning speed is limited by that of single task training. Yet other methods train a new model for each task, but this is infeasible in true lifelong learning over hundreds of tasks. Our method takes advantage of single model approaches for faster training while exploiting the higher flexibility of multi-model methods. Let's begin by formalizing our problem setting. In RL, the agent is faced with a Markov decision process and acts according to some stochastic policy pi parameterized by a vector theta. PG learners optimize the expected long-term returns by following the policy gradient. In lifelong PG learning, the agent will be faced with a sequence of MDPs and will strive to optimize the returns across all tasks. The agent will be allowed limited experience on each task and must leverage accumulated knowledge to quickly learn a policy for the current task. Now let's look at our concrete algorithm, lifelong policy gradients, faster training without forgetting. Our key assumption is that the policy parameters are factored into a shared repository of policy factors L and a set of task-specific coefficients ST that combine factors from L for each individual task. Imagine, for example, training a robot dog. At some point, the robot may have learned policy factors to move its front legs, bark, wag its tail, and move its hind legs. These reusable factors enable the dog to quickly learn to lie down, sit wagging its tail, or even excitedly jump, wreaking havoc when its human gets home. Upon observing a new task, our method first learns to combine existing policy factors via PG learning directly on the task-specific coefficients and keeping the knowledge base fixed. In the second step, we optimize the second-order approximate PG objective around the theta from step 1. This optimization has a closed-form solution that can be incrementally obtained. Intuitively, this step improves the policy factors with knowledge from task T. Steps 1 and 2 assume that the knowledge base already contains useful policy factors. Prior methods typically initialize them with the policies for the first K tasks trained via single-task training. However, this leads to slow learning of the first K tasks and may lead to components containing redundant information. Instead, we train the first K tasks by learning the ST from the current L, and additionally learning an error vector epsilon that finds the relevant knowledge missing from the existing policy factors. Let's take a look at how this works in practice. We first evaluated our method on Mujoko domains with varying gravity and body part sizes. Our method learned much faster than single-task training, converging to better policies. In several domains, EWC, as single model baseline, was faster than our approach. However, in the two most diverse domains, EWC was incapable of learning at all, due to training a single policy for all tasks. Our method's update step, on the third bars, did not hinder performance, while PGLA, a multi-model baseline, suffered from negative transfer on all 6 domains. After training on all tasks, on the rightmost bars, our method still maintained high performance on previous tasks, whereas PGLA and EWC suffered from catastrophic forgetting. We then created a lifelong version of MetaWorld, where a simulated Sawyer arm must learn to manipulate various objects. Among our baselines, only EWC learned in the presence of 10 tasks, and they all completely forgot knowledge from previous tasks with 10 and 48 tasks. In contrast, our method learned faster than single-task training and suffered from no forgetting. To recap, we created a novel lifelong policy gradient method that enables faster training, completely avoids catastrophic forgetting, and achieves lifelong transfer on the recent MetaWorld benchmark.